pleasure to introduce our speaker, who is Valentin Lychagin. He will tell us about dynamics of molecular media and generalization of Navier-Stokes equations. I have two requests. First, we are testing a new device for transmitting audio. So if you encounter problems, kindly let us know. And second, when you ask questions or make your remarks, kindly name yourself, because we don't know everyone who participate in our seminar. So now it's time to begin. Thank you for joining us. I pass microphone to speaker.
Сейчас, одну секунду. Правильно, да? Один очки. Так. So, let's begin. Okay. I would like to present you some development of our group on dynamics in media within the structure, and in particular molecular media. It's my talk based on 3 papers. One paper I will write shortly you can find more about this. It's do you know Lychagin and Lychagin in differential geometry and application, 74, and this year. It's a paper where we introduced geometry and Navier-Stokes equations for media in a structure. Then there is also paper Lychagin. It's symmetry. So it's about it was the question about dynamics of water was really the first and the more important question that I tried to understand. When I was a student, I read Birkhoff's book on hydrodynamics, and I read that, and it was a very big surprise and shock for me that where he wrote that Navier-Stokes equations doesn't describe the water. After this is the question, what they do then if water is not Navier-Stokes equations. And one paper, it's my own. It's strange journal, Global and Stochastic Analysis. It's in the previous year, and this is it's called Kozira media, but it's mainly about also molecular media, and this is in some sense flat, and this is some sense space models. But I will explain it in more detail. So really, more details about what I will talk about, you will find in these papers. And really, I will maybe cheat a little. I will hide some details, but you can find them in these papers. Okay, so let's begin. So I start with a simple, in some sense, situations. It's Navier-Stokes equations on manifolds. So it's the following situation. Assume that we have manifold, and this is Riemannian manifold. And you can think that it's simply a configuration space for some mechanical system. And we take some flow, say X, selector field on M, and consider this flow as a flow of, so elements here we think as the particles. So we have this flow, and we want to write this is Navier-Stokes equation in this setting, not in the situations where we think that particles are just small balls in our standard space, and we discuss the dynamic. Yeah, so X will be just a vector field on M, but to be honest, it should be non-autonomic situation. So X will also depend on T. Then the right vector field should be this one. And how this Navier-Stokes equation look like? It's simply a statement from Newton law, acceleration multiplied on mass equal force. So in this situation, what means force acceleration? So we take nabla, it's a Levitch-Vita connection that corresponds to our metric G. Then this expression this is what we should think about acceleration, right? If we multiply, say, let's assume that, not assume that, let omega g, it will be volume form on this manifold. Let's say it's oriented. And say rho will be a density of our media. Then I should multiply on the volume, so I should multiply here rho on omega g. And this is, you should think as a acceleration multiply on mass, and mass, it's exactly this one. And what Newton law says that it should be force. So here I should write force. And what we know is that this force has really, we have two types of force. So-called surface force and volume force or body force. In standard writing of Navier-Stokes equation, what this is related to, say, pressure, standard setting, and this is just some forces that act on volumes, like, say, gravity. Okay. So what we can say about this and about that, but about this practically nothing. I would only say that it's some density of our force multiplied omega g. It's this guy. And what we can say about surface forces, we should go to my favorite thermodynamics. So let's analyze this one. In some sense, this main term, because the previous stuff is just very elementary. So we will consider thermodynamics as a measurement that I told few times about this. So what kind of quantities we try to measure in this situation? So first of all, it's so-called inner energy, entropy, volume, mass. What else? Yeah, and some huh? No, we don't measure it. Just wait. So and something. This is what we call extension quantities. So extensive means that if you take system and just put it together, then say energy, entropy, volume, mass will be just added. And there are another that called intensive, that when we will just put together this say two bodies, then they will be equalized, but not summing up. So due to temperature, to energy, it's not exactly temperature. Maybe it should be called coolness. It's opposite to T. This guy is, nobody knows what it is. So we have no idea what kind of dual variable should be for this. So for volume, we know it's just pressure. For mass, what is a dual for mass? So sorry, we should go to chemistry. It's so-called chemical potential. And there is something here. So this more or less standard set of variables that we study in thermodynamics. But it has nothing to do with our situation where we talking about this is motion of say of our fluid. So it should be something added from this one. I will take one of them. I will explain later why it is. I will take exterior, no, not exterior, covariant differential of x. It's will be operator. It's tensor. What kind of tensor you get? It will be just t, not this t. So this is a tensor of this form. So t, this is x, and when you differentiate, you'll get this one.
Sorry, just question for curiosity. What is dual to S? It would be what variable to dual to S?
I have no idea what will be dual to S because I have no idea what S is really.
Sorry.
It's a really good question, but instead of S, we should put really information. Then it will be much more clear, but it will be, then my talk will be much more longer. Standard letters that use it here S, so I put it S, but don't ask me what it is.
Okay, thank you. Sorry, thank you.
Okay, I don't want to insult anybody, but it's just honest. So this is really some mysterious notion. We know that it's very important, but what it is, we have no idea. Okay, so there is a relation between these guys. So I will write it like this. It's called first or second law in thermodynamics. So really, it's better to write like this. Delta S 1 divided by T delta E. And here minus P delta V. No, and minus say Y ice dx ice delta x ice. So this is here x ice. don't this one. Okay, maybe it's better to use, oh, then P would, okay, X and Y. So all these expressions you can see just in pairs. So V together with P, X is should be introduced together with this Y's, E together with temperature, one divided by temperature, and this is usually how they write it low in, it's really conservations of energy in thermodynamics. And so I will write like this, but once more, it's when I write D, you should ask me what really D is. It's differential of something. What about this something? Really, this guy should be considered as a, we should take the following space with the coordinates S, E and theta, P and V, Y and X. So this is we know what it is, at least letters. Y and X is still unknowns because we expect that it will be something like this. And relation between these variables, it's really extensive, means that they, if you just take all extensive, they give you vector in some vector space. So this means additivity of them. And dual to them intensives, they will be elements of the dual space. It goes directly from, okay. At least up to now, it's not important for us. I will explain this guy really, and not the thermodynamic itself. So what we will do, it just simply let us, and we have no idea how this related to this. And the main idea is the following. So we will take maximal submanifolds in this phi where this is form will be zero. It's so-called Lychaginian manifold in this space, and this form is this contact form on this manifold. Or it's better because, as I see, S for us is just something not eatable. So let's go to space without S. So take projections where we just simply skip this S. Then Lychaginian will go to Lagrangian. This is not for this, it's just for this one. So this will be Lagrangian. And we call this is thermodynamical state. Oh, this or this, it doesn't matter. But yeah, really, we will work only with this. We will try to escape from using of this S. It's just. It's really, it's not possible to escape completely from S, but at least in these formal constructions that we'll use, maybe we'll try to avoid using of this S. Okay. Now there is one more point here that, as I said, extensive variables means that they just additive. So it means that if you take this state and say if you extend this extensive variable, say multiply on some number, then nothing should be changed in our construction. So it means that there is this transformation where all extensive, say S, E, V, M, and X, you simply multiply by some lambda, say. Then this manifold should be the same. So it's should be symmetry of and they don't change intensive variables, only multiply extensives. So as you know, that in all this is Lagrangian, Legendre, they just it's one jet of some function, and this is simply differentials of functions. And this property simply means that functions that we'll use, they should be homogeneous functions for functions of degree 1 in these variables. Okay, and to avoid this type of transformations, we will go to say, so it's say this manifold L. It will be just manifold of this form. S is some function of this is extensive V, M, and X, and all these variables like 1 divided by theta, it should be F by E, P divided by theta should be F by V, and so on. So just jet of this function. So this is one derivative, this is one derivative in E, this is derivative in V, and this is derivative in X. And this function should be, as I said, should be homogeneous of degree 1. Is simply property of this variable. So we believe they're extensive. So if you just extend all of them on some lambda, it doesn't change our system. And intensive, as we introduce it, this h should be constant. And it's obvious. So if you just multiply all this on lambda and s also multiply on lambda, then derivatives will not change. So it says, okay, how to describe homogeneous functions of degree 1. So you should divide by one of these, say by E, by V, by M, or by some X, and write this function, say the functions of the form, for example, M multiply on some function, and here E divided by M, V divided by M, and X divided by M. And it's doing very often in the thermodynamics of the gases. It's these constructions they call that you go from these variables to so-called specific variables. In our constructions, because we just in situations of field theory, we talk about fields on manifolds, and we know that in this case we describe all these fields by their densities. So it means that it's better to divide by volume. Then this will disappear, and it will be mass divided by volume. So F0. So this is any function, and this is just our function. If you will do this, you can move from this is form to form in this is new variables. I will use a simply small Greek letters for these ones. It will be epsilon, let's it will be mu, and this is for example, yeah. Okay, so what form you will get? Sigma it's taken for this place. Really, I will write not sigma but small s instead of this. So -1 divided by theta, and here will be d epsilon. This term will be just disappear. And here you will get minus, I don't know, say alpha i's d beta i's. Okay. So, oh, I forgot about M. Where is M? It should be here. Really not minus. It should be plus some gamma dm, because M it's also in our extensives. So when you'll divide it, here will be not d beta, but say something like gamma d rho. Yeah, and plus this alphas d betas. So this will be condition for our manifold L or L tilde. So if you factorize by this action, then result of this new factor space where instead of these variables we reduce it variables, this form should be equal 0. And once more, you have either it should be Lagrangian, but it's like Legendrian in slightly different space, or it should be Lagrangian also in slightly different space. The only that we need here, it's understand what it is. Now let's use this observation. So I will put it here, the dual, I will denote it by sigma. I will keep, so it will, I will denote this by delta, this guy, and this is by sigma. In other words, what we trying to measure, we try to measure, this is it's called deformation tensor. We try to measure how our velocity field will be deformed if we just will shift this field in some directions, but shift means that it's used as Levi-Civita translation.
So sigma is due to delta or not?
Yeah, sigma should be, да. So here what we will get. Not exactly. I should take dual. So delta, this is element of this. So this is a dual space, and so you see every time I take some pairing of dual with a corresponding extension. So what should be here now? I should write dual between this delta and sigma. So sigma operator here, but if I take, so we have duality between this. What kind of duality? So how to think sigma as a functions on this? I take sigma, take dual to sigma, multiply on this one as operators, and take trace. So this is a duality between them. And therefore here it should be expression like trace sigma star, or simply sim prime star taken, multiply on the delta. This is just what we try. Huh? Because every time you take differential of now you think that delta is just simply formal operator. It's related. This is how the operator related to our vector field X. But thermodynamics, it doesn't care about vector fields and so on. So it simply means that here we measure of operator, and the dual to this will be also operator, like here. And but in this is form, it will go like this, so like trace of this stuff. Okay. Oh, is it okay? Okay, so we can, okay, let's forget about this. Let's simply count how many variables we have here. So this is dimension of this, it's 2n square, right? Dimension of delta n square, and it's the dimension of our manifold. Sigma also has this dimension, so this is pair sigma and delta give us this dimension, and here you have 1, 2, 3, 4. So 4 plus. So it means that now our phase space is without entropy. It's Lagrangian point of view. So this is space of this dimension. It's symplectic manifold. We should take simply differential of this, and we'll get a symplectic form on 5. And so this L, it should be 2 plus n square dimensional manifold, and this is guy. And so what? Yeah, and Lagrangian. There are some more really structures on this in this situation, but this is the only that I will need. So this is manifold that Lagrangian manifold of this is dimension, and this is what will be described thermodynamics of our media. Now let's see what really does it mean on the practical. It means that we have this number of coordinates on this manifold, and what is this number? As a candidates, I will take this delta. It's give me n square coordinate, and I need 2 more, and I will take one of them. It will be rho, and the second one, I sorry, but I will take delta. It's more convenient. Then this manifold, if these functions are coordinates on this L, it will be described with some function h. Function of this is of these variables, and it's not difficult to say, but I will just to be sure. So you will get the following equation for this L. So sigma, it will be derivative of h in delta, gamma, this chemical potential, it will be derivative of h in rho. Energy, it will be h minus theta h on theta. So this is h, it's white h, it's so-called Helmholtz free energy, but for us it's not important. So this is really description of Lagrangian manifolds where this is functions are coordinates. Then you will get this description. And what is important for us at this one? So it means that if so to define say thermodynamics of our dynamics or our motion, we should introduce this function. And then in terms of this function, we will get all other. So we'll get, I skip energy, so also entropy. So you can find energy, you can find chemical potential, and this is guy. But as we know, this sigma is also tensor. So this is its so-called deformation tensor. And here it's so-called stress tensor. No, it's if you take this say epsilon, rho, and delta, then you're right. but I changed mind and I take this coordinates. Yeah, you should interchange this. So it's simply some trick, but it's much more convenient to use this. But what is important for us? So in our situation, okay, this delta is I remind you, it's simply a differential of our covariant differential of our vector field X. So this we know. What is a sigma, and what is sigma responsible for? It's the following interpretation. Okay, I just remove this one. It's really related to this is surface forces. So assume that we have some surface S. Okay, it's S. Okay, surface. It's not entropy anymore. And at each point, you can take normal to the surface of this normal. And what is a sigma? Okay, if I take not sigma, but sigma star, then I can apply it. So sigma star, it will be simply endomorphism of T. So I can take sigma star, sorry, sigma prime is better. Sigma prime of n, and I will get another vector. If you remember the standard course of, I don't know, geometry or something like this, this is explanation of surface forces. So at each point of surface, you just attach some vector. I'm sorry, I use it for vectors. I will use for forces. I will use vectors. More correctly, they should be covectors, but because here I need vectors, so they will be vectors for me. So, and this is a situation that we have at each point we have this vector, and we think that this chi that acts on this small piece of our surface. So to get what is the force act on the whole surface, what you should do, you should take integral of this sigma prime s ds. I'm sorry, it's too many. So this is say surface, and here differential of this, and this n, and this is pi. So this is how they do in standard situation. So they take this integral, and this integral by using the standard analysis can be transformed to integral over this volume. And if you take divided by this is delta v and go delta v to 0, you will get something that we call force that act on this volume. So force itself act on the surface, but it's also act on the volumes. And so we converted this as surface force in the volume type forces. And in a situation like this blackboard, it will be just simply you take this vector field and you take the divergence of this vector field, and you will get this force. In our case, it's not what means this integral. So this is vector at each point. This is element of the this point P. So at each point, this is the tangent vector to M. So we have here vector elements of the different vector spaces. So it's not we're not able to write this integral anymore. So what we'll do, we take reasonably small this ball, take some, say, center of this ball, and say, take this is like radius. Just say this is geodesic that goes from this point to this point, and take this vector and take parallel transport of this vector at this point. This allows me to identify these vectors with the new vectors. I will put here, say, tilde, and this is the center point C, with elements of the same vector space. So now I will take integral not this type, but I take integral of this sigma prime tilde n dp over p. And now this is an integral, just some vector valued function in this situation. And what we should do, we should simply take divergence of this, the standard divergence, and we will get, if delta v goes to 0, you will get something that we will call, this is surface force. But what essentially we did, so sigma itself has nothing to do with volume. It's just an element of this. So this interpretation of this element as some force that act on the of our surface. We integrate it over this, we get some information how really, what the force act on the whole surface. And this is construction. It's too many words, but construction is very, very, very simple. So let's say, let's begin with a simple situation. Say take a field of operators acted on T. So more correctly, let's it will be elements of vector field, tensor, one forms of. At each point, we'll get element of this form or this form. Because we in matrix case, so you really can identify all of this by using the same metric. Now we just will repeat this trick with the deformation tensor and apply once more. This is differential, covariant differential of A. What we will get? It will be this one, tensor of the same type. And because differential, you should multiply on omega 1 more. So this construction that we just did, blah, 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 it gives us vector. So now I just play the game. Okay, I take the differential, I get this type of tensor. The question, how to get vector from, yeah, how to get vector from this? Yeah, maybe I should change my mind. I will take. So it's like sigma. It's endomorphism of this, and this is, as we know, it's T star tensor T. So this one. So this is our E. I take differential. I will change now omega 1 here, dm here, and omega 1 no, I cannot avoid the problem. Okay, I will back to this notation. So this differential as before. What I will do now, I will take contraction of this and these two elements. So C1, 3 contraction. Just spherical this one. And result give me covector or differential form. Yeah. But we need vector. So how to get vector? So we take our metric G minus 1 and you will get vector now. So let's call this, say, we use it bemol there, but it's very difficult. Okay, I will write G minus 1. So this construction, we take this one, take exterior covariant differential, get this one, take contraction, and get apply our metric, and you will get a vector field. So let's call this diff A. So the elementary really exercise, just check it that this vector that we get by these manipulations, it's exactly this one. So it's exactly, if you take this as sigma, our sigma prime, consider as this operator here, and take this integral divided by delta v, go to delta v to 0, and you will get exactly this one. So it means that this one, we know what it is. It's simply divergence of this sigma prime. And this is its body forces. Okay, they may be presented like gravity, or they can be we can avoid them. It's some extra forces that we cannot get in from this picture. But this is just, it goes directly from this thermodynamics. So on practice, it means the following. So you have some media, with your points in M, you consider the media. They just made from some physical objects. And there is some thermodynamics that rule by this media. And as I'm sorry, it's very short, but I don't think I need to say more. This thermodynamics described by this Gellerhorn's function. And this is in some sense, it's hidden here, because when I say simply particles, 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 I did not make some assumptions what kind of media we have in hands. And this is, at least this is says as what kind of thermodynamics this media has. And this is this function. From these functions, you can find, by the derivations, you can find the sigma. Now, really, I prepare a formula for this divergence. It's a long formula. If you wish, you can check it yourself. In coordinates, it's you should be honest. So you should write this differential, take this contraction, take inverse, and blah blah blah, and you will get finally this formula for divergence. But one important remark. So this will be sigma. It will be function that depends on what? On temperature, on density, and on our delta. And our delta, this is differential of x. So to take this divergence, we should differentiate components of A. To take A, we should differentiate components of x. So this term that we added here, it's second order differential expression. It can be linear, can be non-linear, depends really on our media. Okay, so it is really the main equations that I wanted to present you. Yeah, there is another consideration of conservation of mass. It's better to write in short form this equation. So this expression we will write as a DDT. They call this material derivative on x. I will divide by volume form, because here I should also multiply by volume form. And this is body force, density of body force. So this is Navier-Stokes equation. And also it's called also conservation of momentum. There is also conservation of mass. It's and if you just look at this, so the first equation, so how many equations we really need? Okay, we want to find x, so we need at least the same number of equations at dimension of x, so n. But here we have n equations, right? To find this sigma and stuff like this, we also need these coordinates. We need theta, rho, and delta. Delta we know because it's just given by the differential of x. So we need also two equations that related to theta and to rho. So this is equation for rho. So this for rho is for x, and we need one more equation. And this equation should be for one of these thermodynamic quantities. I take temperature, but you can take, instead of temperature, say energy or entropy, it doesn't matter. So at least you will get here something like this. For example, on energy. And this is conservation of energy. It's not important to use the conservation of energy because, as you see, we have this set of thermodynamic variables. So yeah, you can use it these ones, or you can take instead of temperature, you can take energy. But what you know, I think you know, that if you have Lagrangian manifold, then coordinates of this Lagrangian manifold, they can be just given by some number of, say if it's in classical mechanical notations, Q and P. So then coordinates in Lagrangian manifold given by some number of Q, this is coordinates in some number of momenta, and they should be complementary. And this is just, there is a theorem that you can cover any Lagrangian manifold by this type of coordinates. So this is exactly what I did it here. So this is theta, it's just by assumptions that it's complementary to, we need to, this is n squared plus 2, so n squared plus 2. And here should be something to say, we can put here sigma or say gamma. It's not a good idea. We should get something else. Anyway, this equation can be not only for energy. As I say, it can be for entropy, it can be for temperature, and etc. Yeah, it really depends on what kind of thermodynamics you have in hands. Say, if you know that you can describe everything in terms of this epsilon, rho, and delta, then you use it, this type of equations. Okay. Есть. Сколько у меня времени там еще? Полчаса. Ага, я еще не начинал рассказывать. Yeah, okay. So it's just not short, it's a long introduction. It's how to write Navier-Stokes equations. Say this is mass conservation, so continuity equation and energy conservation equations in general setting. But I hope that you will like this expression, especially if you compare with the standard expression for Navier-Stokes equations. They're so long and it's very difficult to understand what they really meant when they wrote them. Okay, now I will make the next step. Sorry, I forgot to say this about this function h, what it was, rho, theta, rho, and delta. There are so-called Newtonian media. It means so all these guys, so theta and rho is just simply some quantities that have no relations with our manifold, but it has relations because it's element of endomorphisms of T. Our manifold is Riemannian manifold. We have here, this is metric G. It means that on this space, we have action of orthogonal group of G at the point. Not on the whole manifold, but thermodynamics is every time it's not related to manifolds, it's related to only points. So just this one. Okay, so Newtonian media simply claim that this guy should be invariant under this action. It doesn't touch this components, but it transforms only on the delta. So you can simply think the simple function on endomorphisms. In other words, we want to take quotient. Okay, let's say it doesn't matter. We should take this quotient and say that this is Helmholtz functions should be functions on this quotient, so should be invariant under this one. Now let's go to linear algebra. So the question very simple. Okay, you have Euclidean space, so T is Euclidean space. You have operators on this Euclidean space, but yeah, I have a linear operator, and you want to know how the orbits of these operators with respect to our orthogonal group. We know about SL or GL. It's what we learned at school. What we know, if say delta will be a symmetric operator, then we also know, that if you have symmetric matrix by orthogonal transformations, you can move it into a diagonal form, right? But now we cannot say, and we will see that really in applications of this picture to this media with structures, this will be just not symmetric operator. So the question, what is the invariance of this? So there is it was, as far as I know, Artin formulated as a conjecture, and Procesi proved, but not only this, for different groups. So they claim the following. So if you take, say, I will, instead of delta, will be write A. So A is this element of this. We can write the following expressions. Yeah, certainly traces their invariances without problem. So we take trace A in some degree alpha 1, take adjoint A prime with degree beta 1, and so on. Say A in degree alpha m and in A prime in degree beta m. So let's call this as P. It's after Procesi, and here alpha beta. Alpha beta is this multi-indices. So let's write like this. But here it's product. So what really Procesi proved is that this is just this set generates all invariant polynomials, SO invariance polynomials on endomorphisms of T. In our case, it means that this function H, it should be function of H, theta, rho, and this is Procesi invariance. It's conditions that we consider media that is homogeneous on the infinitesimal level. So if I will rotate, then my say thermodynamics will be not changed. My media will be, my material will be not changed. Huh? We should say take all possible alpha and beta such that their lengths not more than 2 in degree n minus 1. Yeah, but it's no. It's a standard question in invariant theory. If you have action, say in this case, you have action of semi-simple group, say, then you expect that all invariants will be polynomials. Gilbert. Yeah. And this is just a set of generators in polynomials. Really, there is this Rosenlich theorem that claims that we need much less. It's the following, that it means that if you compute the dimension of this, you will get that it's n plus divided by 2. But it's very easy. You should simply subtract dimensions and you will get this number. So it means that we need really this number of rational, it doesn't matter, rational, polynomial, but independent. So this is a manifold. It's a really algebraic manifold, an affine algebraic manifold. And to find atlas on these manifolds, you can use some coordinates, and you need this number of functions, either polynomial or rational. It's up to you. But this is how to describe orbits. Yeah, it's no need to use all these polynomials. You need much of this. Okay. Yeah, but it's Newtonian media, and there is another guy. It's a hook. It's required that this is function. You can really express energy also in terms of this function, but dependence on this is delta, on this deformation, it should be quadratic. It's like hook laws also. If you say move to your point on the distance x, then energy of this should be x proportional to x squared, maybe with some linear terms. So it means that if you write like this, then we should take only such polynomials where this function will be quadratic, and then you will get the following expression for h. H, it will be, what is this? Yeah. 1/2 some a on trace delta square. I will write simply lattice, but it should be function on rho and t. Plus b trace of delta or delta prime plus c trace of delta prime square is a quadratic term, and plus linear term, it should be, no. Trace in square, and plus linear term, it will be d trace of our and plus e. So this is only such functions that satisfy this GDEq proposition, so that energy should be quadratic in deformation. So A, B, C, D, E, they all functions of rho and theta. Yeah, it's a joint. Because T star, yeah, no, okay, but it's up to you. Yeah. Okay, so this is Helmholtz functions that satisfy Newton conditions, that it's invariant of orthogonal transformations. Is the second is Hooke conditions that they should be quadratic in deformation tensor. Where, yeah? Huh? I'm sorry. Yeah, and if you just take this type of media, and this is the standard choice of media in continuous mechanics, then you will get expression for sigma very simple. So sigma, it is, where is my sigma? A delta conjugate plus B delta plus C trace delta and plus D. So under this is two Hooke and Newton requirements, we see that our relation between stress tensor and deformation tensor it's contain not four, yeah, 1, 2, 3, contain four functions. These three functions, it's so-called viscosities. This one is corresponds to so-called pressure. And now there is one point, and it's point really cheating point in continuous mechanics, and also in my talk. This pressure, what about this? What is the relation between this? It's maybe you remember from initial courses in physics, there are inertial mass and gravitational mass, right? And at least Kikoyan, who he taught me physics, he just explained me that during war they make about kilometers deep hole and try to compare inertial mass and gravity mass. And it was done in the middle of Siberia, because if just 100 kilometers from this hole will be just simply some car will be just moved, then it will be destroyed completely. Experiment. It's very subtle experiment. But in our case, we also have two absolute measures, and this is really, guys, that appears when in the following phenomena. Then our say this media moves, then the volume will be just changed during this motion. And if volume of our media changes, then this pressure, it corresponds to change of this volume. But this pressure, it corresponds to change of volume, but not stable volume, but volume of media in motion. And it's completely different physical situation. So this is just how you measure this. You should take a piece of this media, put it here, and start to play it, I would say, change, for example, volume, and see what's going on with what is the reaction of our, say, body will be if you change volume. So what kind of force you will get. But it's completely different. It's also related to change of volume, but in completely different situation. So in standard settings, they simply put it pressure and think that it's exactly the pressure that we use it here. I put letter D. Yeah, possibly it's the pressure that we use it here. Possibly it's true that pressure will be not dependent. Take the say body, and we take this body start to move. So this is the same pressure. Yeah. It seems that it's right, but personally, I cannot really prove it. Simply, you either believe or agree with this or not. Anyway, if you don't care about this one, you really care about this one. Where is our H? Yeah, this one. Because it's really give you complete description of your thermodynamics. And this is the coefficient, this D, will be just pop up here. And you see that it's related to trace of this. And trace is simply divergence of our vector field X. So it's really show you how so delta itself is a differential of X, and if you take trace, you will get divergence of X. Okay. Okay, now I will stop here, and we just will go to what I promised to in the structures. So So we assume that our media build it from some, say, particles or infinitesimal small bodies, and it can be just not point for us, but it may have some structure. I just will give you some examples. So in other words, I will assume that this manifold is a total space of some bundle, say over B, and with some fiber, say F here. So B, we will think as a, I will assume that this microparticles, they are still rigid for us. And this corresponds from M to, so this is just this cloud of this some like molecular, some microparticles. And this map, you take this as guy and take this as center of mass of this. This will give you just point B. Say if you just take simply some reservoir with a molecule in space, then B will be just our space, three-dimensional, and this fiber, it means the following. So I fix center of mass, and we'll consider all possible position of my microparticles with assumptions that they have the same center of mass. So it's like in a degree of in the freedom selected here. So I will continue to use assumption that M is a Riemannian manifold. V, it's say over M. B also will be Riemannian manifold, but with a B. And this also will be, fibers will be Riemannian and with a metric GF. So everything Riemannian here for me. Maybe I will start with some examples. Question? Between what? No, I don't know. Not yet. It's not the final point. I will just add some more geometrical constructions to this. So let's assume that this is our microparticles. They like rigid bodies. So if you take rigid body and take center of mass, then you consider all possible positions of this rigid body, you will get SO3, right? So this is center of mass, and here you have simply SO3. Or maybe O3. It depends on what kind of, do we have oriented, this is body, or we have non-oriented body. It's, you'll see that it's related to so-called chirality in physics. It's very important construction. But let's assume that's simply SO3. So it means that if you consider this microparticles such that they on the micro level they're like rigid bodies, then you will get the following fiber: your manifold, here fibers SO3, at least not SO3 but SO3 act there, right, and act in transitive way. So it's not exactly SO3, but it's space where SO3 act in transitive way and effectively. Okay, and this is here, say, some domain D in R3. So this is just situations when in some domain D you have some set of macroparticles, say small, say like sand, for example. So this is our situation. It's so it's, I call this Kozira media. Now maybe 200, yeah, 2 centuries. It was brothers, Kozira brothers in France, and they investigated dynamics of media where these particles, like I said, rigid on the micro level. Honestly, I never understood what they wrote about this, but the idea was of this type. Okay, it's the first example, and example number 1. It was really initiated all this activity. It's how to describe, say, water. What we know about water. Okay, my considerations will be pure mechanical, so I will not go in quantum mechanics stuff. It's pure mechanical. So this is molecule of water. So this is how geometrically it looks like. This is our O, and this is 2 H's. And this is this triangle, and this triangle inside our space. So how to fix this triangle? You should fix this plane, but plane itself, it just you can define, say, by orthogonal vector, right? So to fix plane, it depends on if you have oriented planes, then you need element of, so this will be element of sphere, this vector, right? Or you need maybe element of projective plane if it's not oriented plane. What else? On this plane, okay, this is just fixed. It's very heavy, so let's think that this our image, but we have also these 2 B's, the two H's, this one and this one, and we can rotate now this triangle inside of this this plane. So how this look like? It's the following. So we still have this projection, but I will just simply describe this as a fiber. So first, to fix this is plane, we should take a sphere. Now the plane that we take here, it's orthogonal to this vector. Then it should be, we can consider like this. So this is my sphere, this is my vector, and this plane, it's simply tangent plane to sphere. And now on this plane, I can rotate it. So it means that I should also fix a angle of rotation. So it means that I should take here a circle inside of this. Then it will be give me complete description of my picture, at least for this one. It's not for this, but it's for this one. So it means that we have this fiber, and this fiber projected on 2-dimensional sphere, and fiber of this projection is circle. And this is what they call a spherical bundle that corresponds to tangent bundle. So if you have many manifold, Riemann manifold, you can take tangent spaces and take their spheres. And this gives just this one. It's better to write the dual description, not this vector, but not tangent space, but cotangent space. Then it will be much more better description. So we have this cotangent space of sphere, but here we should take all covectors of length 1. So this is say G equal 1. So this surface. So in another way, it's you should F is just something that defined inside of this cotangent bundle, and given by equation, say, length equal 1. Really, any constant, it's not, but it's not important. So this is another construction. So it's also, this is M over this, but here you have this description of this fiber. One more example. It has very scaring name. It's binary gases. Say, take for example this one. So it's just one or another or. So this is the center of mass. So really, to define this, I simply should fix a line inside of space, right? So it means that I should take, say, bundle over D, say, doesn't matter, tangent or cotangent, but I should take these lines, and this means I should take prerequisition of this. Or T star, it doesn't matter. But there are binary gases, what they call homogeneous, heterogeneous, or no, homogeny and heterogeny. So if it takes something like this one, then one of the C and another like one O and one C, then it means that in this case you can take that this oriented line, and then you'll get what we should write, a circle bundle of this prerequisition. Here's the circle bundle. But what is important, if you will assume that all these constructions they on the micro level rigid, it means that on all these guys we have action of SO3. But this construction is really not complete, because yeah, we know that SO3 act on these micro elements, but it's very possible that these elements they have some symmetry. So there is some, say, finite group and inside of SO3, or it depends, or O3. It's a group of symmetries. So if it's inside of SO3, then this fiber will be SO3 divided by this group, say group G. If this group, then it will be O3 divided by this group G. It's very remarkable groups. Yeah, there are some number of trivial these groups, but there are extremely nice groups. It's symmetry of Platonic bodies. So the biggest group that you can find is a group of A5, and also there is S4. And what is funny is that at least I look at in this chemistry books, there are really molecules that have exactly this symmetry groups. Yes, write me name. I will give you answer the next day. There are simply atlases of these groups. One point important here is the following: that there are molecules that have symmetries inside of O3, namely symmetries that invert orientation. And there are say molecular or media where we have only symmetries inside of SO3. So this called chirality, and this is achirality. So it's chiral, and this is achiral media. Chirality, you know that this name goes from Greek name for hand. So it's handed and non-handed molecule. So, and we have we have two hands. In some sense, they're symmetric, but the symmetry between them, it invert orientation. The funny thing is that really, say water, there are different types of water. And say there are water, so this is say right orientation or left orientation. So with chirality, so without, or achiral or chiral. And it's how they found. So really, if you take water, inside of this water can be really molecular with chirality and without chirality, achiral. So really, it consists of two types of molecule. And for water, maybe it's not so dangerous, but they first they describe this. It's two types of medicine. One is penicillin, and the second I forgot it. It's for pregnant women. So they noted that sometimes this medicines that they gave to their patient, sometimes it was very nice, and everybody will happy to use this medicines. And sometimes the result was simply dangerous. Say for pregnant women, it was tragedy. So it means that inside of, say, I don't remember, our body contains 80–90% of water. And the question, what kind of this water, how many chirality there, and how many achirality there, and possibly that you know this fairy tales about dead water and live water. So possibly there is some interaction between them, and possibly some processes inside of our bodies also depends on this correspondence. But it's a slightly different point of view, because if you have, say, full water and it contains two types of components, say, with chirality, without chirality, then really it's what they call, in our favorite activity that we just doing with this gas and oil, it corresponds to multi-component or multi-phase systems. So, and then really motion of water, it's not motion of only, say, water of chirality or without chirality. It contains both of them, and you should also take in consideration interaction between them. But I will consider now only chirality, so only inside of SO3. I will not care about this O3 case. And then this is in the structure spaces that define really in the structure, they just this quotient as SO3 by some finite group. It's as you know, SO3 is a three-dimensional projective space, and this is factorized projective space by action of finite group, say symmetry of some Platonic body. And we will see that it's extremely important for us, because when we just will write all these equations, it will be just part of these equations will be just live on such very nice quotients. Okay. Now I am going to write this. I will talk only about Navier-Stokes equations, but it's very straightforward to write these also equations. So I will consider this is bundle M, F, and B, they all have some metric, some Riemann structure, because it's you see that all of them, they just correspond to some mechanical systems. I say that I consider only mechanical part of the bodies. So it means that all of them have this kinetic energy, so you can have this matrix. Is the first one. So now what is will be motion for me? This will be vector field X, but on this manifold. So it means that when our media moves, what's going on? It's motion of beats, it's motion of center of mass, and also there is some motion in fibers. It's like some kind of rotations of inner structure. So it will be our X, but before to do this, I will add one more geometrical structure to this one. It's the following. So take, say, some of this micro element. So this is center of mass of this, and just move it in some way in B. So our media, there are two situations. One, it will not change the inner structure, so it will not rotate our element. So in some sense, media will be neutral for this inner structure. And another way, if you just will do this on M, when you take into account inner structure, on M you will get some transformation. Another way, it means the following. So if you have here vector X, say vector V, then and you move your element along this V, then will be some vector there that corresponds to reaction of our media on this motion of this particle. Without all this it's easy to say that you have your bundle and you have a connection on this bundle. It means that if you move here, then this will be just a lift of this motion center of mass to motion of our particle. So this will be the second ingredient. So we have this is a bundle of Riemann manifolds, and to this we also add this one connection in this bundle. Then I am ready to say what is the relation between all this is metrics. I will take metric here, GB, and say this is tangent plane to M, and here just horizontal vectors. So this is horizontal. So I take this GB and put it here because it's isomorphism between this space and tangent to B. Also, there is also fiber here, and on the fiber I have metric GF, and now I will assume that these two subspaces, they just orthogonal, and metric on GM, it will be GB plus GF. But plus, if you just take this as connections, it's plus in terms of connection. Okay, and now we are ready to write our equation. So I take vector field X on M, and this vector field, and I will require that it's not arbitrary vector fields on M, because it should describe motion of these particles. So it means that it should be projected to motion of the center of masses and some rotations in states. So I will represent this as a some vector field x0, and this is vector field on B. And I will lift it, this vector field, with help my connection H, and plus another vector x1. And this vector x1 is vector that vertical to tangent to fibers. So this is will be vectors or vector fields that will describe the motion of our media. So x0 responsible for motion of center of mass, and this is responsible for rotations. Huh? Yeah. Любое. Нужно, чтобы сохраняло расслоение. Yes,
Bundle.
this is will be not. It
It's
will be
a bundle.
horizontal vector field, but not vector field on this one. Если оно проектируется. Yeah, so это как условие, чтобы оно сохраняло это расслоение. Вот если оно расслоение, ну, как бы в смысле расслоение, это и есть наша это самая среда. Поэтому мы ходим, если движение, то оно, конечно, оно не разрушает наши молекулы, там оно просто движется. In other words, so this is our representation of this vector field. So now we simply write this is Navier-Stokes equation for this x. It will be very special. I just will tell a little about this. Really, this is description of this sigma, and description of this Helmholtz functions will be different, because now we cannot say that our functions, as Helmholtz functions, should be invariant under rotations. Not all rotations of this, because there is this decomposition. So at least it should preserve fibers. We cannot remove fibers from consideration. And it gives you a slightly longer description of this Helmholtz functions. But if you take this Newton conditions that it should be invariant under orthogonal transformations that preserve the fiber, it's the same conditions that vector fields preserve bundle, and also this group conditions that this function should be quadratic in deformation tensor. And you can see that really deformation tensor also will be not arbitrary matrix. It will be something like this, something here, and here 0. It will be like this. But anyway, fortunately, it also belongs to Processi. We can find all invariants in this classification, write the form for Helmholtz, and write this as condition for, like we have this one. So once more, we should repeat it, everything that we did it for manifolds, but for this special case. And this function, okay, it will be quadratic function. It will be not three coefficients, at least in quadratic part. It will be more. I think it's 6, something like this. So it means, and it's more or less understandable because it's some kind of viscosity along base and along fiber. So there are different type of viscosities here. But anyway, you will get the same. The equation will be the same equation. F, it's once more, it's some Borti forces. It's simply forces that act between our, say, microparticles, and they depends as a position of the center mass and depends on position of your in the components, so on rotation, say. And here we have two types of interesting motion. The first type is horizontal motion. So if you take simply x1 equals 0, take simply x0. So it gives some equations very similar to this, but we should be careful. I just will say about this. Just wait a minute. And in other motions, it's motions where x0 equal 1, but we have only x1. It's like a frozen media. So the center of mass, it will be not moved, but inside of this media, we will have some kind of rotations. And then you will get, this is Navier-Stokes equations, or this is nice quotients. Okay, and what else I want to say? At least the detailed formulas and blah, 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 you can find in these 3 papers that I listed at the beginning. What else? Yeah, I think it's more than enough. Отдать тебе это самое? Только...
Okay, thank you very much. Any questions, remarks? No question? Yeah, no remark. Okay, thank you very much again. So we meet next time purely in Zoom. We have a talk by Professor Yuri Sachkov on some matters related to sub-Riemannian geometry, and you're welcome to join this seminar. Goodbye.
Thank you for invitation. Oops.